Then this is logistic. Take off the two headers that's left over from before. The new one is logistic. We are going to compare it to the recursive exponential. So here is the recursive exponential, right? Isn't it the previous value times 1 plus r? Isn't that what we did right here? Previous value times 1 plus r. So this is just comparing it to exponential. This is not the new formula yet. If you did that and you distributed, you'd get the previous value plus the rate times the previous value. You guys catch that?
Yeah, absolutely.
Okay, previous value plus the rate times the previous value. So all I'm saying is take the formula for exponential recursive and distribute. Okay? Questions on that? I'm taking this formula from last time and going and rewriting it. The reason I want to do that is this basically turns in to the new formula. So here's the deal. This is the old formula. This is the new formula. The new formula is previous value. So previous value, oh look, previous value, plus the rate, okay, plus the rate times the previous value. Well, this purple part and this are the previous value in the new formula. So it's the same idea. It's the previous value plus the rate times the previous value. But it takes more to get the new previous value. So it's just this formula beefed up. Okay? If you want to ignore that, you can and just say, okay, here's my new formula. Fine. Here are the pieces. Okay? P to the n minus 1 is the current population. It's the previous value, but I'm not going to give you an explicit formula for this. Okay? It's just too confusing. There is no, for as far as you're concerned, explicit formula for logistic growth. We can only look back at the previous value and find the next year. I can't say it starts here and 20 years down the line I know it's going to be this without actually looking at every single one. Okay? R is the base rate of growth and K is the carrying capacity. And what I mean by carrying capacity is here, okay, we have these guys stuck on an island. There's no way it's going to grow this fast. There is a limit to food. There's disease. The fact that it's just dudes stuck on an island, right? They're not going to grow exponentially. At some point, the island's going to say, I can only support 5,000 dudes. That's the carrying capacity. Okay, so your population can grow up to 5,000. Once it gets a little high, okay, lack of resources, disease, whatever starts to kill them off, then they'll grow again and they kind of will stay around 5,000. So that is why you notice here in this actual graph, it grows a little slower than our model. And then when it hit the carrying capacity, what is the carrying capacity according to this graph? Somewhere a little lower, somewhere in here, it's asymptotical right in here. It got about 150, 160 and started to go back down because the island could no longer support that many men. Okay, so, or limit, because the real world can only support so many people, so many animals. And what I was showing up here is this is the old formula distributed, has the same pieces in the new formula, except for we had to add a part right here to help with the limiting. That's all this is an extra piece to help limit the growth rate. Because once you get too close to what the island or the population can be sustained, then the growth rate is going to slow down, and that's what this piece does right here. So now we need to use it. It says, go back to the desert island example from last time. Here's the explicit formula. Okay, an exponential explicit formula for the desert island example. Okay? Suppose we say that 9 million and 4 trillion are not reasonable, because last time up here, okay, we've got these big amounts of people. It is not reasonable amounts, okay? And instead, we estimate that the maximum sustainable population on that island to be 1 million. Okay, so that is going to be our carrying capacity, is 1 million. Well, we're going to then have a new growth rate. So here, isn't the growth rate 0.0171? We're going to change our growth rate, okay, using this formula. This is the rate of the logistic equation, okay? The rate for the population times the part that limits it. Okay? So that is right here. The rate from down here times this part that is going to limit it will make it the new rate for the logistic equation. All right, so let's do this. If the original population, wherever we're starting, we were at 39 people. We're so many years in, right? The original population is 100. So I don't know, maybe that's n of 5 or whatever, I don't know. That's pretty small. If I want to find the growth rate for 100, okay, I put the rate in. Now again, we are looking at the one from right here, right? Actually, we are looking at, oh, I apologize. It's this one all the way over here from last time. And this is where we said 9 million and 4 trillion didn't make sense, right? At the end of last class, we said that's not even close because the world population is only 7.442 billion. These two don't make sense, so we need to limit it. I apologize. It was looking back there. You guys good with that? Okay, so that's where I got this formula. I pulled this from last time. If we're at a point where, yes?
So why is that equation? I thought there was an explicit equation.
This isn't an explicit. This is a piece of the recursive. So what they're saying is if we were going back and looking at this one, okay, it's going to grow like this. But the closer we get to the carrying capacity of 1 million, it's not going to grow as fast. The growth rate's going to start to slow down. So what I'm trying to find is the new growth rate. If I was, let's say right here, if I was here at 100, it's still growing really close to 1.71% a year because it's way far away from the carrying capacity. As I get closer to the carrying capacity, it's probably not growing at this rate anymore. Maybe it's only growing at 1% a year because we're starting to max out the resources on the island. So what the formula is right here is just what's the rate at a specific point along that graph. And the closer we get to the carrying capacity, the lower the rate. Does that make sense? So this is just a piece of the new formula. In particular, this right here is the same formula as this. Okay, and that is right here. The book has P. It's saying the population now. But really, once you plug it into this formula, it's saying the population before what you're looking at. So this formula, it's just this yellow piece of the big formula. It's the new rate. Okay, so here's the deal. If we're at 100, we're still really close to the starting number of 39. So we're going to plug our rate from yesterday, 1.71%, times 1 minus where we're at 100, divided by the carrying capacity of 1 million. Okay? And when you crunch that, our new growth rate is 1.7. So to start off with, as this population grew, it was growing at 1.71. Now we're not that far away from the start, so it's just still growing at the same almost, 1.7. It just lost a little bit. How do you guys feel about that? Okay, this is how quickly it's growing now when we've moved a little bit farther into the population, a couple of years in. Okay? What if now we have 900,000 people on that island? Really close to the carrying capacity of 1,000,000. We've almost reached the capacity of the island. Another 100,000 people and this island cannot support them. Is it going to be growing as fast? No. So how fast is it growing? It's only growing 0.171%. Here it was growing 1.7, and now it's not even growing a whole percent. Yes?
So in problems like this, will it give us the original R, or will we have to find that?
I have to give it to you. What they'll say is, given that the population is this, and the carrying right now is this, and the carrying capacity for the island or whatever you're talking about is this, find the new R. Okay, plug it into the formula. Now notice, guys, 900,000 divided by 1,000,000, isn't that almost 1? Right? When you get to 1,000,000 over 1,000,000, wouldn't this become 1? 1 minus 1 is 0. And all of a sudden it says now the growth rate is 0. So you're heading up to a growth rate of 0 because the island can only handle so much. Now in the real world, you might actually pass this carrying capacity for a little bit, but then people start to die off. Okay. So you could actually end up with a negative growth rate for a while. All right. So here's the deal. If somehow magically they dropped a bunch of sailors on that island, 1.1 trillion, that island cannot support 1.1 trillion, right? So what is my new growth rate? It's now negative. People are dying off at a rate of 0.17%. It's called overshoot and collapse. It overshot the carrying capacity of that island, and now the population is going to collapse back down to, or the population is going to collapse back down to where the island can support people. Anthony, go get a drink. Go get a drink. Okay. So all this was doing was finding this piece of this formula. So they'll ask you these questions in two ways. They'll say, here's where we're at now. How quickly are we growing? That's this formula. Or they'll say, we're here this year. Find the next year. That's the whole formula. So we now need to do a couple of those. And I want to go back. I know this is not the picture, but notice this one kind of did an overshoot and then collapse. So when I asked you guys what the carrying capacity here was here, and you said 160,000, and I said, no, maybe it's a little lower, it's because it overshot and then started to go back down. Probably would kind of collapse. It might even actually be something over here. Okay? Because sometimes there's a population boom and then it doesn't sustain. And I'm thinking more, humans, we manage to make it sustain. We send in humanitarian aid, etc. But you're talking about a deer population in the forest, it's going to follow this type of trend. It can only support so many deer. All right, so here's a picture. Okay, so here is your population. Starts to grow, but then it starts to level off as we hit the carrying capacity over time. The other thing that could happen is it grows, it overshoots, collapses, and starts to level out. So ideally it's going to do this, but in the real world it might be a little uglier. It might overshoot and collapse back to the sustaining amount. Okay? And then this graph says, as the population gets bigger, your rate of growth is going to get smaller, right? Start out with a high initial growth rate, lots of food, lots of space, and as you start to use up all of that food and space, you do not replicate as fast.